I'm Sabrina Keil and I'm a PhD student at LMU Munich. Welcome to my presentation. Through the recent development of portable rotational sensors, there's a variety of new applications opening up. I'm going to present one of those applications for the co-located recording of the 3 translational and 3 rotational motions generated by seismic waves. I want to show if it is possible to retrieve the 1D velocity structure of the shallow subsurface using such single-station 6-component measurements. In addition, I want to compare this new method to the approved approach of array measurements. Since there are many situations in where an array setup is difficult, such as in urban environments, a single-station approach would make measurements a lot easier. The work presented here is part of the so-called SIGA project, which is concerned about the monitoring of deep geothermal power plants and the possible seismic effects. As part of the project, I wanted to do microzonation for the inner city of Munich. So, first of all, what exactly is microzonation? The goal of seismic microsonation is to estimate the wave velocity of the shallow subsurface. Here we speak of the approximately upper 100 meter. The reason is that the local velocity structure can strongly influence the shaking characteristics of an earthquake. Hereby, the local geology plays an important role. For example, soft sediments, which are low velocity features, can amplify the waves and therefore cause more damage to buildings compared to constructions on firm bedrock. And that's why we have to get more information about the subsurface. So how are we going to estimate the velocity structure? First of all, we're measuring seismic noise, which was generated by human activity, such as traffic or constructions. Seismic noise mainly consists out of surface waves, meaning loft and Rayleigh waves. The most common method to measure those signals are array measurements, where you set up a number of stations, usually in a circle as shown here. Now, the velocity and the direction of the wave field can be estimated through the different arrival times of the wavefront at the stations. Here in our study, we're analyzing the array data using frequency wave number analysis, but other approaches exist, such as the spatial autocorrelation. These array methods are well established and give reliable results. However, their installation is very complex, and that's why a single-station approach would make measurements more convenient. In the field of microzonation, such a single-station approach already exists. It's the horizontal to vertical spectral ratio method. These H-to-V ratios can be interpreted as the ellipticity of Rayleigh waves and are computed by taking the horizontal over the vertical component of particle motion. It was shown that such H-to-V curves exhibit a pronounced peak close to the fundamental S-wave resonance frequency of the site, as shown here. Since this is a single-station measurement, installation is very easy, but its theoretical foundation is still not completely understood and the results suffer from non-uniqueness. And that is the reason why we are working on a new single-station approach. We're using so-called 6-component measurements where you record 3 translational and 3 rotational motions. In this case also we're recording surface waves, and the particle motions that they are induced are shown in this figure. Loft waves cause a transverse particle motion and induce a rotation around the vertical axis, while Rayleigh waves cause an elliptical particle motion and rotations around the horizontal axis. Now, by exploiting the relation between translational and rotational motions, the phase velocity of the surface waves can be estimated. For example, for a plane fundamental loft wave, the phase velocity can be computed by taking the ratio of the transverse acceleration and the vertical rotation rate. In addition, you need a scaling factor of 1/2 and a minus because the motions are anticorrelated. As you can see, the phase velocity is frequency dependent because surface waves are dispersive. That means for each frequency band, the phase velocity can be computed, which results in a dispersion curve. This dispersion curve is then inverted to finally obtain the local velocity profiles. So let's look at the instrument setup. For our method, we need 2 instruments which are placed on a common monument very close to each other in order to record the same motion. So it really can be considered a single-station measurement. In our case, we're using a trillium compact seismometer in order to record the translational motion, and the blue size 3A rotational motion sensor in order to record the rotations. The blue size 3A is the first commercially available broadband rotational sensor, which is based on a fiber optic gyroscope. The great advantage of the measurement principle of such a fiber optic gyroscope is that it's strictly insensitive to translational motion. That guarantees that pure ground rotation is measured, which is great. In addition, laboratory experiments have shown that the blue size has a flat self-noise level in a broad frequency range compared to other sensors. Also, it's very stable in changing ambient conditions such as temperature and magnetic field, which makes it suitable for field installations. Our study area is Munich's inner city in Germany because here a new geothermal power plant could give rise to induced seismicity in the future. In addition, Munich is situated in the Molasse Basin and is therefore underlined by thick layers of sediments, which could amplify the waves as I've shown in the beginning of this presentation. Because of that, it's important to do microzonation, but at the same time, we're inside a large city, so setting up an array is not always that easy. So in the following, I'm going to evaluate if our 6-component method gives comparable results to this array measurements. Here I want to show you a direct comparison of the instrument setups of the two methods. This is a measurement that we did at the exact location where usually the Oktoberfest takes place, because here we had enough space to set up the array. For the array, we used geophones, and in order to record a large frequency band, we need to set up 3 different circles with different diameters. The smallest circle had a radius of 6 meters. Here you can see the circle with 18-meter radius, but the largest one had a radius of 50 meters, so it was even bigger than this. And compared to that, our small installation for the 6-component measurement. So it really gets clear that such a single station approach is a lot easier to perform. In addition, our 6-component measurement takes only about 2 to 3 hours to collect enough data, while such an array measurement can easily take up to 8 hours, including the setup of the different circles. Alright, let's look at the results. First, I want to show you a result for a measurement that I did at the geothermal power plant. As I said, through the relation of translational and rotational motion, the phase velocity can be estimated. Here you can see the resulting dispersion curve for love waves using the 6-component data. Normally, the phase velocity increases with decreasing frequency, as is the case between 20 and 5 Hz. But then suddenly we see that the velocities drop again, and this should not be the case. So the question is, where does this come from? To answer this question, let's look at the power spectral densities of the recorded data. The 3 upper traces belong to the translational motion, and the 3 lower traces belong to the rotations. There are a couple of things that we can note. First of all, the translations are larger than the rotations, which is expected. And second, the energy content decreases with decreasing frequency. The problem is that at some point, in this case at about 5 Hz, the self-noise level of the blue size is reached, and therefore no actual ground rotations are measured, but only the self-noise level of the blue size. And that's why the curve is flat in this range. So that means the ground rotations are too small to be measured by the sensor, and that's why the dispersion curve drops at this point. This means now we can only use the data in the range of 20 to 5 Hz, which would give us the problem that we cannot invert to the desired depth of 100 meters, because for this we need lower frequencies. And that's why we now complement our dispersion curves with H2V ratios, which give us usually data in the lower frequency range. The good thing is that these H2V ratios are computed by only the 3 translational components. And since they're already included in our measurement, this method basically comes for free. Now let's look at some direct comparison of the dispersion curves from the array and the 6-component method. This is the result for the Oktoberfest location. We can see that the 2 curves intersect in a certain frequency range, but the 6-component data give us information to higher frequencies up to 20 Hz, which means we could resolve the shallow subsurface better. while the array data gives us information to lower frequencies, which means we can look deeper into the subsurface. And again, we see that the 6-component curve drops at a certain frequency, which again represents the limitation of our sensor in those low frequency ranges. In the next step, we take those curves and invert them in order to obtain the local velocity profiles. In case of the array data, we use the Rayleigh and the loft dispersion curve as input data, and in case of the 6-component method, we use the loft, the Rayleigh, and the H2V curves as an input parameter. Then we perform the inversion. In our case, we constrain the inversion to a 3-layer model and link the P to the S velocities. As a result, we obtain the local P and S wave velocity profiles. Here I've only shown the S wave velocity profiles as a comparison. The colors represent the misfit of the different computed models, and since we want a low misfit, we're looking at the yellow models. We can see that both profiles look quite similar. In both cases, the profiles reach a depth of 100 meters, as we wanted, and we see 2 velocity steps. The upper one lies at about 5 meter depth, and the second one at about 30 to 35 meter depth. In addition, the velocities are also quite similar. In both cases, the lowest S-wave velocity we reach at the surface is about 200 meters per second, which is quite small, so indeed there could be an amplification of the waves. But this is under investigation in an ongoing study. In the last step, I wanted to see where those velocity steps come from. So I compared the velocity profiles to lithologic profiles that were generated from borehole data. We can see that the upper velocity jump coincides quite well with the groundwater table. And the second velocity jump lies in this range of the sandstone layer at 30 meter depth. So the groundwater as well as the change in lithology can influence the wave velocity, and it correlates quite well with our results. Alright, let's wrap things up. We've seen that the 6-component method indeed gives us comparable results to the array measurements, which is great because we've seen that single station approaches are a lot easier to perform. Even though we saw that there's a limitation of our method in the lower frequency range due to the sensitivity of the sensor, we can overcome this limitation by complementing the dispersion curves with H2V ratios. This 6C method is useful in many situations where an array setup is difficult, not only in urban environments, but also, for example, at the ocean bottom or on other planets.